Good morning, guys. My name is Daniels. I've been presenting my final report for project number one, which is about analysis of automobile suspension systems. Um, so the use of this project or this given system that I'm proposing is meant to be used as an improvement in performance to automobile suspension systems as they confront all-terrain conditions. A suspension system is designed to ideally improve comfort and road handling abilities. Uh, I defined previously the different types of automobile suspension system in my abstract presentation. So, but here I explain further which the type of suspension system we have is the leaf spring, we got the McPherson strap, and we got the double wishbone. And let's focus on the results of this project, which is first of all we did some assumptions that consider a basic spring damper system with a spring and damper constants as K1 and Bay1 for passive case. A quarter of the sprung mass acting on one spring damper system is M1 and the unsprung mass being M2. In our analysis, we have considered the tires as a combination of spring and damper, having coefficients as K2 and B2. Taking all the motion in the vertical direction x-axis, let M1 move x1, M2 move x2, and the base road excitation is W. The input excitation in the form of a step input. The entire calculation is done on one spring damper system, such that only quarter of the mass is to be considered in the analysis. So we have the passive case and we have the semi-active case, which we're gonna be like comparing both and analyzing. So the data we picked for the project was the quarter car sprung mass, which is M1, 241.5 kilograms, M2, the unsprung mass, 41.5 kilograms, K1, which is the spring constant, 6,000 Newton meter, and K2, the equivalent tire spring constant, 140,000 Newton meter. Like B1, the damper coefficient, 300 Newton second meter, and B2, equivalent tire damping coefficient, 1500 Newton second meter. We got the PID controllers coefficient as proportional gain, KP, we got 0.552, in interval gain, KI, we have 5.52, and derivative gain, KD, 22.08. This is the governing equation that we are using, which is for the linear spring damper system. And then we apply the Laplace transform for the given equation. We get this these three transfer functions. And then I did a Simulink block diagram in MATLAB for the passive case. And then we have the Simulink blocks for the nonlinear or semi-active case using MATLAB as well. So these are the responses I found when I plot the results. We have the sprung mass displacement versus time, comparing linear and nonlinear cases. And we have the pink plot, we have the passive case, the yellow plot is the semi-active case, and the green one is the road input or excitation. So we see here that in the passive case, the maximum overshoot of displacement was 0.0712 for a passive case, and a semi-active case, 0.0076, which was reduced by 89.32%. The settling time for passive case, we had 7.08, for semi-active, 2.32, which was reduced again by 67.23%. And the rise time for passive case was 0.3099, and for semi-active case 0.2014, which again was reduced with 35.01%. We got the suspension travel. We got pink plot is the semi-active case, and the yellow plot is a passive case, which is a constant damping coefficient. For this time, in the passive case, the maximum spring compression was about 0.177, and semi-active case was 0.0693, which was reduced by 44.12%. The maximum spring elongation in meters for the passive case was 0.0683 versus the semi-active case 0.007172, which this time was reduced by a bigger number, 89.49%. So here it's clear that the implementation of semi-active suspension system has brought down the maximum expansion and compression of suspension spring by a huge amount, minimizing the possibility of a spring failure due to fatigue loading. So the tire deflection, in the pink plot, we have the semi-active case, and the yellow plot, we have the passive case. This time, and the maximum tire lift from the ground in meter for the passive case was 0.0231. For semi-active case was 0.0131. So which resulted in a reduction of 43.2%. We can conclude that in semi-active case, the tire lift from the ground as well as the setting time is much less in comparison with passive case. In here we have the sprung mass velocity versus time for linear and non-linear case, where we have the pink plot is semi-active case, and the yellow plot is the passive case, which has a constant spring coefficient. So here also, although velocity overshoot is high for PID controller, but it still lasts for an extremely short period of time, which once again make it a better option. We have, what else? We have the sprung mass displacement for an inclined ramp and a slope of 30%, 30 degrees. We have in pink, we have the passive case. In yellow, we have the semi-active case, and the green is the raw input. So it seems that in semi-active mode, the response syncs with the input, giving maximum comfort. We have the sprung mass response for an arbitrary excitation. And we got here again, the pink plot is the passive case, yellow plot is semi-active case. And once again, the above graph, output maximum overshoot response for semi-active is much lower than the passive case, which conclude that is much comfortable than passive case. So as conclusion, we are in this report, suspension is designed for a quarter car model of a passenger car to improve the ride comfort and roll ability. For PID controller, Ziegler and Nichols tuning rules are used for a series of tuning to improve the ride comfort and roll holding ability. For step input, the 0.1 meter, the sprung mass displacement has been reduced by 89.32%, which shows the improvement in ride comfort. The maximum suspension compression and elongation has been reduced by 44.12 and 89.49 respectively. The tire deflection has been reduced by 43.3%. Also, the sprung mass setting time and rise time decreases by 67.23 and 35.01 respectively. Even for inclined ramps and an arbitrary excitation, the output response is much desirable for PID controllers as compared for the passive one. Therefore, it is concluded that semi-active case suspensions system has better performance capabilities over passive suspension systems. And that's my project basically. Thank you guys.